class yesterday, what's the purpose of simplifying radicals? And the answer, it was you, Brent, so we can get a standardized form of the answer. So that a student in China and a student in the United States and a student in Africa, we're all getting the same answer to the same problem. Because there's an infinite number of ways that you can write something like the square root of 8. We could write this in an infinite number of ways. Right? You could write it as, does anybody have an equivalent form for this?
2 times the square root of 2.
Yeah, that's the simplified form, 2 square roots of 2. What's another way we could write it?
Decimal.
A decimal form?
1/2 times the square root of square root of 32. That's exactly right. Square root of 32 over 2 is correct. Now what Jackson did is multiply this by 2 inside and out. Right? What's 2 inside the radical? If you put 2 back in a square root symbol, what do you have to do to it? Square it, right? So it's the square root of 4. So it's the square root of 32 over 2. And if we don't simplify that, we don't get to there. Okay? So there's lots of different ways you could write this. Wilson?
The square root of 2 times 2 times 2.
That's just that. That wouldn't be a different form. That's just a different way to write 8. That's still the same thing. Yeah, so we want a standardized form. Just like we want everybody to reduce fractions, we want everybody to simplify their radicals. Now, simplifying radicals takes a different twist when we're learning to simplify quotients involving radical expressions. Now, we have multiplied radical expressions, we've simplified radical expressions, and today we're going to divide radical expressions. Okay? Now, there's a couple of properties that we're going to do here, and then we're going to talk about another form. This is another form of things, and this is equally dissatisfying as simplifying radicals is. It's a skill, all right, and it's a skill that's again directed at making sure that everybody arrives at the same answer, same form of the same answer. Okay, so simplifying quotients involving radical expressions, we're dividing radical expressions is what we're going to be doing today. Now here's a couple of important concepts. An expression with a radical in the denominator isn't considered simplified. It's an important fact. In other words, if we had 2 over the square root of 3, that's not simplified. Why is it not simplified? Because it has a radical in the denominator of the fraction. Now, this is true of any radical, so we're not going to limit this to square roots. Cube roots are not allowed in denominators. Square roots, fourth roots, fifth roots, any radical expression in a denominator is not allowed. It's not meaningless. Your calculator would give you a decimal value for this. It's just not considered a proper form. Okay, so that everybody arrives at an answer that looks the same, we're never going to leave a square root or a cube root or any kind of radical expression in the denominator. Something like this is also not allowed. Why is that not allowed? Because it has a radical in the denominator. Okay? A radical in the denominator is considered not simplified. Okay? Another thing is fixing this situation where you have a square root or a radical in a denominator is called rationalizing the denominator. So we only want rational expressions in denominators. We don't want any irrational numbers like the square root of 7, square root of 4, square root of 5, square root of 3, square root of 2, square root of x. We don't want any of that left in the denominator of a fraction. We want only rational values. All of our radical expressions, our irrational numbers, we want to be in the numerator of the fraction. Okay? So that's the goal that we're working with. This entire lesson is geared toward this skill. This skill, pay attention. All right? getting our irrational expressions out of the denominator of the fraction. Okay? So we have the square root of 7 over 3. The directions here say to simplify. And normally with a fraction, what does that mean? It means reduce the fraction, right? Okay? But we can't reduce 7 over 3, can we? So in this case, this is applying to this new rule that I just told you. An expression is not considered to be simplified if it has a square root in the denominator. Does this have a square root in the denominator? It does, right? What's the square root in this denominator? 3, right? Square root of 3 is in the denominator. So we've got to do something to get rid of that 3 in the denominator. What can we do?
Multiply the top and bottom by 3.
Multiply the top and bottom by 3. Now technically, we could talk about 7 over 3 inside, or we could talk about 7 over 3 outside. But if we're going to introduce something to the outside of this, I can't multiply it by 3, can I? What can I multiply it by? I can multiply it by the square root of 3 over the square root of 3. Now we could go inside and multiply by 3 over 3. That's the same thing, right? So what will that give us? Square root of 21 over the square root of 9, which is 21 over 3. Now, can I simplify 21 into 3? Why not? Because one's rational and one's irrational number, right? You can't multiply or divide rational with irrational. They don't mix. There's not a 3 in the numerator of this fraction. There's a square root of 3 up there, because the square root of 21 is the square root of 7 times the square root of 3. There is no 3 up there that can cancel with the 3 in the denominator. We got rational and irrational, and those two cannot mix by multiplication or division. So that's a pretty simple prospect, right? Okay, let's have a look at another one. Simplify square root of 5 over x, and again here it's telling us to assume that all variables represent non-negative numbers. All right, why is that important? Right, when you take the square root of it, it can't be negative. That's one reason that this is important. What's another reason it's important? What kind of number is 5 over x if square root of 5 over x if x is negative?
Irrational.
It's imaginary. All right. Now, imaginary numbers, we haven't talked a whole lot about the rules for working with imaginary numbers, but there are some subtle differences in how you work with imaginary numbers and how you work with real numbers. It's okay to multiply real numbers that are in square root symbols. The rules are different with imaginary numbers. Okay? You have to make the radicals real before you can multiply the imaginary numbers. So it's very important that we know we're working with real numbers here, and it's very important to know, as Brent said just a second ago, that what we're working with when we take the square root is going to come out as a positive value. Okay, so those two concepts there are extremely important. So what can we do here to get rid of that problem? What is the problem? Buster? What's the problem here? Do what now? Yes, it's telling us that we've got a square root of x, right, in the denominator of a fraction. How can I get rid of that? How can I make it go away, Buster? Multiply top and bottom by the square root of x is correct. And what will that give us on the top? Square root of 5x. And in the bottom, it gives us the square root of x squared, which is just x. Because x is positive, it's just x, right? If x weren't positive, then we can't even work this problem the same way because we just multiplied by an imaginary number incorrectly.
How is that simplifying?
It's really, like I said at the outset of the lesson, very non-satisfying. Does this look any simpler than what we started with? It actually looks more complicated, doesn't it? All right, it's just considered a standardized form. Now, this skill that we're learning here, this rationalization skill, is extremely important for calculus and for limits, some of the other concepts that you'll learn when you take calculus. Being able to rationalize things is important. It's important for, well, I can't really explain it. I mean, I can explain it, but not in such a way that 13 of you would understand it. Okay? Maybe 17 of you. A couple might. All right. But anyway, it's dissatisfying. It's just a skill. The end game is getting rid of the square root in the denominator. Okay? Now, here's another one. Now, on this one, we're going to employ a different property. Quotient property of radicals. Okay? The quotient property of radicals says that the quotient of square roots is equal to the square root of the quotients. All right, so here's what we can do. Here's what we mean. What I mean by that: the square root of a divided by the square root of b is equal to the square root of a divided by b. So we can take those two radical expressions that are separated and we can put it all under one radical. Okay? That's what this property, the square root property of quotients, says that the quotient of square roots, this is the quotient of two square roots, is equal to the square root of the quotient. Yes, George?
Are we not able to do that with this problem because 3 is outside of the...
Well, the 3 stays outside, and we're just going to kind of treat the 3 as something that's just a little bit of a nuisance at this point. The 3 is not a problem, is it? What's the problem in this? What's the problem here? The square root of 20x cubed is the problem. Okay. Now, we can do something with the square root of 20x cubed by rewriting this fraction as 3, hold on just a second, 1/3 times the square root of 72x to the 4th over 20x cubed. Now, how does this help us?
So cancel x.
We can cancel the x's, right? That helps us. We could also simplify 72 over 20 if we wanted to, right? What goes into both of those numbers?
36 and 2.
What goes into 72 and 20?
4.
4 goes into 72 18 times. 4 goes into 20 5 times, and I've just got an x there. Because x to the 4th over x to the 3rd is x to the 1st. But we haven't completely fixed our problem, have we? What's the problem? This problem that the mathematicians have created by giving us a rule on how they want this answer to look means I can't have that square root of 5 left in the bottom. So what do I have to do with that square root of 5? Multiply top and bottom by the square root of 5, right? And this 1/3 still just hanging around. 1/3. Up top I've got what?
90.
Square root of 90x. In the bottom now I just have 5.
Why does it do that?
Why does what do what?
Like, when you do square root of 5 times 18x over 5, like, why does it cancel the square root at the bottom?
Because 5 times 5 is 25. and the square root of 25 is 5. But the property here, the property that's at play here is that the square root of a times the square root of a is always equal to a as long as a is positive or equal to 0. It has to be non-negative. So if you multiply the square root of something times itself, it just undoes the radical. The reason it does that, Brent, is because of what a square root is. Let's go back a few lessons. Remember that the square root of a is the same as a to what power?
1/2.
1/2. Okay? So squaring that thing is the same as multiplying 1/2 times 2. What's 1/2 times 2? It's 1, so it gives you a to the first power. Okay, so to counteract a cube root, you could cube things, right? So they're inverse operations of one another because a cube root is 1/3, and multiplying 1/3 by 3 gives you 1. All right, we're not finished with this problem. Let's go back to where we were. What do I have to do now?
Take out the perfect square in 90.
What is the perfect square in 90?
9.
9 times 10, right? What's the square root of 9?
3.
3. And so I'm just going to rewrite this. We could probably skip a step here if we wanted to, but that's 3 times the square root of 10x over 5. And now, what happens? The 3's can cancel. Their factors, common factors can cancel. And we're left with the square root of 10x over 5.
It might be too long.
This the next application of this that we're going to look at, guys, is going to require us to have a look back at another important concept. And that important concept is what happens when you multiply something times its conjugate. So what do we get when we multiply 3 plus the square root of 5 times 3 minus the square root of 5? Everybody write this down and work it out. 3 plus the square root of 5 times 3 minus the square root of 5. Okay? Savannah, what do we get here?
4.
You get 4, right? What kind of number is 3 plus the square root of 5?
Irrational.
It's an irrational number. 3 minus the square root of 5 is an irrational number. So we can multiply two numbers and get two irrational numbers and get a rational number. Now keep in mind, what we're doing here is called rationalizing the denominator, which means we want to get rid of any irrational expressions from the denominators of our fractions. No radicals, no square roots, no cube roots. We can't have any of that left. All right, so let's have a look at another one of these. What's the square root of 2 plus 7 times the square root of 2 minus 7? It happened again, didn't it? What's the answer here?
Negative 47.
Negative 47 is the correct answer to this one. Now, what is the relationship between 3 plus the square root of 5 and 3 minus the square root of 5? They're conjugates. Square root of 2 plus 7, square root of 2 minus 7, they're conjugates. All right, so the concept that we have to have here as we move forward is when you multiply an irrational expression by its conjugate, you get a rational number. So an irrational number times its conjugate gives us a rational number. Brent, what's your question?
The slide back there, why would it be minus for the first one?
Why would what be?
On the slide, like Okay.
I don't know if I can.
Yeah, why is that 4? Why is it not 9? The first one.
3 times 3 is 9, right? Negative 3 square roots of 5 and positive 3 square roots of 5 cancel each other out. Square root of 5 times negative square root of 5 is negative 5. So we've got 9 and negative 5, which is 4.
Yeah, I missed I forgot to multiply the positive square root of 5 and negative square root.
Yeah, so what we're going to do here, guys, is rationalize. Again, this says simplify. What's wrong with this to begin with? It has a square root in the denominator. So what we might try to do is multiply top and bottom by the square root of 5, but that won't work, will it? Because we have to distribute the square root of 5, and that would leave us with 3 square roots of 5 plus 5 in the denominator, and the problem is still there. Okay, so we're going to recall what we just practiced again and talked about earlier in the year. If you multiply an irrational number by its conjugate, you get a rational product. Okay, so what are we going to do in this problem to rationalize the denominator? What are we going to multiply by?
Multiply the numerator times 4 plus the square root of 5 and the denominator by 3.
No. We can't do that. We're not allowed to multiply.
Oh, that's reciprocal.
The only thing we're allowed to multiply by is 1. Buster? We multiply the top and bottom by the conjugate of the bottom, which is 4 minus the square root of 5. Okay? This is not intuitive. This is something you have to remember. To rationalize the denominator, you multiply it by its conjugate. It works even if it's square root of 3. Conjugate of square root of 3, you could multiply it by negative square root of 3. Or you could see the square root of 3 as square root of 3 plus 0. So what's the conjugate? Square root of 3 minus 0. So, I mean, the concept always works, even if you're dealing with a single term. But it's required if you're working with a binomial expression. Yes, Brent?
Why would you 4 plus square root of 5?
We'll look at that in just a second. Let's finish this. 3 times 4 is 12. 3 times negative square root of 5 is negative 3 square roots of 5. And in the bottom, we're going to have 16 minus 4 square roots of 5 plus 4 square roots of 5 minus the square root of 25, which is just 5. And you can see that the irrational terms cancel each other out, and we're left with 12 minus 3 square roots of 5 over 11. Okay? Okay? Is that everybody good with that? Now, Brent, what you get if you multiply 4 plus the square root of 5 times itself is these two pesky terms hanging around. 2 4 square roots of 5. What is that? It's 8 square roots of 5. So we still have a square root of 5 left, and that doesn't fix our problem. So to get rid of an irrational expression, you're going to multiply top and bottom by the conjugate of that irrational expression. So in this case, we have 2 over square root of 3 plus 1, and I need to get rid of square root of 3 in the denominator. But that square root of 3 is attached to that positive 1. So what am I going to multiply by here to get rid of the square root?
Square root of 3 plus 1.
That would work. That would work. But it's going to be a little cleaner if we multiply it by what?
Square root of 3 minus 1.
Square root of 3 minus 1. What you just said would work. It's just kind of awkward to have that leading term as a negative. Square root of 3 minus 1 is what we're going to deal with here. So up top we will have, bless you, we distribute the 2, right? That gives us 2 square roots of 3 minus 2 And in the bottom, we have 3 minus 1, right? Which is 2. Now, are we finished with this? Which 2's can cancel?
Oh, the two that's attached to the 3.
I thought it was part of the term.
Aha! Savannah is correct.
You can factor out 2.
Those 2 things are in the top are terms. So, in order to cancel the 2, we have to use our GCF, right? So we factor the numerator. We factor the 2 out of the numerator, and we're left with 2 times the square root of 3 minus 1 over 2. Now that pair of 2's are factors. They're being multiplied. So I can cancel the 2's, and I'm left with square root of 3 minus 1. Which is what, George?
What?
What was the answer?
Oh, I square root 3 and just subtract it from
What'd you get?
0.7320508.
Does it stop there?
Oh, well, no. The 7 steps. This also.
It stops there in your calculator, but does it stop there? It's an irrational number. So y'all listen. Everybody listen. Listen. The best we can do in our calculator here is a 10 decimal place approximation. It's best that the calculator will do for us. Now, for most practical applications, that would be fine. But just when we're manipulating numbers, this is the exact value. Now, what this exact value is a mystery. It's as much of a mystery as what is the exact value of pi. It's a non-repeating, non-terminating decimal. It continues forever without repeating or stopping. And so, in most cases, they're going to want the exact value of this thing. Okay? So y'all understand the name of the game here? What we're doing in this lesson is rationalizing denominators, making the denominators not have any irrational expressions in them. Okay? Your homework is page 694. Look, we're 694. We're going to finish the textbook.
That's a lot of homework.
Yeah, it's a pretty sizable assignment.
Are we still live?
Now, listen, it would not make sense to wait until Monday evening to do this. You won't remember it. You'll waste your time. Do it today. Do it today. Y'all have a great weekend and make wise choices.